Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Lalo and I'll be walking you through the chemistry course. In this particular lesson, we'll be considering the types of reactions. As these chemical reactions. Yeah, when we talk about chemistry, we know we have to work with reactions and all of that. So in this lesson, we'll look at types of reactions as our first topic. Then we'll consider the oxidation, reduction reactions. Then we'll look at oxidizing agents and reducing agents. Then electrolytic, oxidation and reduction, and finally balancing redox reactions. All right, let's begin. When we talk about the reactions, everything we do in chemistry is all about mixing things together, and there is a kind of a chemical reaction. Although sometimes we do have physical mixtures, that is two things that are mixed together but not chemically combined. But whenever we're talking about chemical combinations, we're talking about chemical reactions. So there are different procedures, different methods in which this can happen. One of such is what we know as the combination reaction. Just as the name suggests, two things coming together to form a new substance. A very good example is when we have hydrogen coming together with water, with oxygen rather, to produce water. This is a combination reaction. A particular thing mixes with another particular thing and a new product is formed. Also, we have what we know as the decomposition reaction. Decomposition reaction is simply a particular thing breaking down into two or more substances. For example, let's take an example of calcium nitrate. Calcium nitrate, when it is heated, it decomposes to form calcium oxide plus oxygen plus I think this is 2 oxygen balanced. Okay, we can have 2 here and then there will be 2 here for the equation to be balanced. So we have calcium nitrate. When heated, it decomposes and it gives up oxygen as well as nitrogen for oxide. We also have what we know as the displacement reactions. Displacement reaction has to do with one element displacing another element in its position. Peradventure, you have something like sodium bromate reacting with chlorine. Sodium bromate reacting with chlorine, it will give you sodium chloride, and bromine would be available. This is aqueous, this is gas, this is aqueous. So that's how it works. You see, the chlorine replaces bromine. Now this happens when one of them is higher than the other in the electrochemical series. The one that is higher, either in negativity or positivity, that's electronegativity or electropositivity, will displace the one that is of a lower level, depending on, of course, what is more paramount in their own group. So in this particular case, bromine is more electronegative. Chlorine is more electronegative than bromine, so it displaces bromine and replaces it. It maintains its position. There's also what is known as the double decomposition. double decomposition. Double decomposition happens when two different substances are together and they switch components, the switch parts. I think a good example would be let's have sodium chloride and aluminum nitrates. Silver nitrates. When you react these two together, sodium chloride and silver nitrates, you would have I think silver nitrate here. You would have sodium nitrate plus silver chloride. You see, the sodium maintained and lost its chlorine to that, while this one grabbed the chlorine but lost his own nitrates to sodium. So that's how it works. One person loses, both of them lose something, and both of them gain other things. We also have what we describe as the catalytic reaction. Catalytic reactions. In the catalytic reaction, it's just like a conventional reaction, only that something is required for the reaction to occur or to be faster, or to a catalyst is being introduced into the system. So that makes us ask ourselves, what is a catalyst? A catalyst is a compound which is involved in a particular chemical reaction, so that it makes the reaction occur faster or even occur at all, and it is itself not depreciated or diminished in the course of the chemical reaction. In other words, a catalyst is a compound which does not take part in the chemical reaction but helps the reaction to occur at a faster rate. So, peradventure, an example of this can be the reaction of carbon dioxide with water to produce water should be 6 and this should be 6. It should produce simple sugar and liberate oxygen. Yeah, correct. So this particular reaction requires sunlight for it to occur. So a catalyst may actually not necessarily be something that is chemically described. We also have what we call the reversible reactions. Reversible reactions. Reversible reactions are reactions that can go forth and back. They can go forth and back, whichever one the environment is conducive for, that's the one that would occur. So we usually use the symbol of an arrow, half arrow, and an half arrow, and pointing in the two directions. Those are what we call reversible reaction. We'll also talk about another one we have, which is thermal dissociation. In thermal dissociation, you use heat to separate two things from each other. And the final, not the least, that we are discussing and we'll be discussing in more details is the redox reaction, the oxidation reduction reaction. The reduction oxidation reaction or oxidation reduction reaction. I will be discussing that more in this particular lesson. Okay, in this lesson we have introduced what reactions are and the types. So before we go any further, In a few seconds, some questions will be displayed on your screen to test your understanding of what has been taught in this lesson so far. Please answer them, and when we get back, we'll concentrate on redox reactions. Alright, let's discuss the oxidation reduction reaction. What do we mean when we talk about oxidation? Oxidation simply talks about the removal of electrons from a particular system, but oxidation can be defined in several different ways. The easiest way to define oxidation is simply the addition of oxygen to a particular expression or a reaction. The addition of oxygen to a particular reaction. What happens when you add oxygen to a particular chemical? Let's say calcium in its natural state, and then you of course, calcium in its natural state doesn't carry any ion. Then when you expose it to oxygen, it will give you calcium oxide, and now this calcium will now be +2 and this will be -2. So this calcium at this particular point in time has been oxidized. It has been oxidized. Oxygen has been added to it, so it has been oxidized. Another definition of oxidation can also be the removal of hydrogen. The removal of hydrogen. In the case of compounds such as H2SO plus chlorine. Of course, we know chlorine can displace this, and that will give us HCl, 2 of that, plus sulfur. Now you see this sulfur here has been oxidized. How do we mean it has been oxidized? It has lost some hydrogen. It has lost some hydrogen. So we'll say it has been oxidized. Another way to check the particular oxidation of a substance is to also consider the introduction of a more oxidizing substance, or a more electronegative substance to the reaction. They introduce a more electronegative substance, that is adding a more electronegative substance to the reaction. Peradventure, we have something like hydrochloric acid, and we react hydrochloric acid with potassium to give us 2 KCl plus hydrogen gas liberated. Now this is also an oxidation process. It's also an oxidation process in the sense that a more electronegative substance has been used to displace the less electronegative substance. Of course, if we even look at it also, it is still as well a removal of hydrogen from the system. Apart from that, we can also describe the oxidation as the addition of electrons. The subtraction, removal of electrons, the loss of electrons. Of course, when you add oxygen to a particular thing, what the oxygen will do is to steal some electrons. So, peradventure, you have your FeO, and it undergoes a particular process, and then it stops. Your ion 2 stops becoming ion 2. That's Fe2 plus, changes and becomes Fe3 plus. It changes and becomes Fe3 plus. Obviously, an electron has left this particular atom, and now that's why it is in 3 plus. So we can also agree also that this is also an oxidation reaction. Well, this is what we could describe as half equation. This particular equation can be fully expressed in something like Fe, let's say 2Fe chloride plus chlorine. This is a solid aqueous. Well, when it is bubbled through, we'll have to. So let's ignore these states. So this is the full equation. While this is an oxidation, this is a reduction. So what is the reduction process? The reduction is the exact opposite of oxidation. So which means it is the removal of oxygen, it is the addition of hydrogen, it is the gain of electron, and also it is the removal of or addition of less electronegative substances. The addition of less electronegative substances or removal of more electronegative substances. So this is basically what oxidation reduction reactions is all about. Let's look at what oxidizing agents and reducing agents are. On your screen about now, a definition of an oxidizing agent would be displayed. An oxidizing agent is a substance which accepts electrons, while a reducing agent is a substance which donates electrons. So that's what we see come to play. We see one of them accepting electrons, we see the other one giving away electrons. The oxidizing agent comes and it comes to take away electrons, just like this chlorine is doing here. This chlorine here is an oxidizing agent, while this iron chloride is a reducing agent, because it is the one giving away the electron to this particular chlorine. So this particular chlorine is here to steal electron, so that the ion now changes from ion 2 and becomes ion 3, because it has lost one additional electron. It changes from ion 2 to ion 3. Let me do a quick recap so we will not get lost about how come we're saying loss of electron and it is changing from 2 to 3. Remember that electrons are negatively charged, and your ion naturally would have been neutral charged if it has not lost any kind of electron. But being that it gave chlorine 2 electrons, so that chlorine can be stable, so it has become +2. Now at this +2 state, this ion still decides to give another chlorine one more atom. It's giving another chlorine one more atom. Oh, this is chlorine 2. It's giving another chlorine one more electron rather. So when it's giving another one electron, it becomes Fe3+, not 2+, because it is losing a minus. It is losing a minus. It is like -2 +2 minus -1. +2 minus -1. It is giving away -1. So +2 minus -1 will become +2 + 1, which give us +3. So that's how we go about the calculation for whether it is an oxidizing agent or it's a reducing agent. An oxidizing agent will increase the positiveness of the other element or the other substance, while a reducing agent will reduce the addition, will reduce the plusness or addition of the other substance. So when we're considering oxidizing and reducing agents, we earlier defined oxidizing agent as a substance which accepts electrons, and we described reducing agent as a substance which give away electrons. Of course, in a particular chemical equation, with some most times when we have oxidation, we have a reduction action following it, because an electron is being given out, something is giving out the electron, therefore that thing is going to be losing electrons. So it happens simultaneously. All right, let's take a look at some of the properties of oxidizing agents and reducing agents. The first thing we notice is that an oxidizing agent is an electron acceptor. It accepts electrons, while the reducing agent is an electron donor. It gives away electrons. We also have an oxidizing agent is a reduced substance. That is, at the end of the whole process, the oxidizing agent would have been reduced. Of course, your reducing agent is an oxidized substance. At the end of the process, your reducing agent would have been oxidized. And also, oxidation number decreases along the positive direction. Oxidation number decreases along the positive direction, while in the reducing agent, oxidation number increases along the positive direction. When you are, I'll take an example here. Okay, don't worry, we'll explain that further when we work with FE. Let's look at some of the ways to test for oxidizing agents and reducing agents. To test for oxidizing agents, you test it by the action of the reagent. You pass the reagent over iron 2 chloride. Iron 2 chloride. Iron 2 chloride naturally exists in a green coloration, in a green color. But by the time you pass the substance and oxidizing agent through it, it will change color from iron 2 chloride to iron 3 chloride, which is brown in color. So there will be a change in color from green to brown if the reagent is an oxidizing agent. In like manner, when you pass the substance also over through hydrogen sulfide, hydrogen sulfide would precipitate to deposit out sulfur components, which are yellow in color. Sulfur particles would be dissolved out of the substance. So it would be dissolved out of the hydrogen sulfide. So when you pass it through, you have sulfur being dissolved out to show you that it is an oxidizing agent. It will remove hydrogen from the sulfur. So in like manner, we also have the reactions for testing reducing agents. We see that in this particular reaction, potassium manganate, which is also known as potassium tetraoxosulf manganate 7, which has a blue coloration when it is purple coloration rather, when you pass a reducing agent through it. We observe that the manganese changes from the state of +7 to +2, and also to test the manganese is of course the +7 state of manganese is in purple color, while the +2 state is actually colorless. While in also the potassium chromate, there's potassium heptachromate 6. Potassium heptachromate 6. We have the liquid. If we pass a reducing agent through it, it changes from its orange coloration to a green coloration. We have it changing from orange to green. Let's take a look at this particular third point that I was talking about, that I said when we look further. All right, if you see, according to this, when you take that iron was having an oxidation number of +2. When it loses an extra electron, it has a next oxidation number of +3. 3 because it has lost an extra electron. But in this place, manganese, which originally had oxidation state of +7, it gains electrons and then reduces to an oxidation state of +2. So this one is oxidized, then therefore the oxidation number reduces in the positive direction. It decreases in the positive direction. We'll talk about the oxidation number decreasing. It does not necessarily mean that you are having lower values, but it is decreasing because electrons is being lost, while this one is increasing because electrons have been gained considerably. Electrons have been gained. All right, let's go ahead and look at electrolytic oxidation reaction. So let's consider electrolysis, oxidation reduction in electrolysis. In electrolysis, we have a setup. We'll look at electrolysis shortly in more details. We have a setup of an electrolyte and 2 electrodes. One of them is the anode, the other is the cathode. At the cathode, electron is given off, while at the anode, electron is accepted. In the cathode, we experience some deposits, yes, because electron is lost. So we can say that at the cathode, oxidation happens, while at the anode, at the cathode, reduction happens, while at the anode, oxidation occurs. So during electrolysis, at the cathode, reduction occurs, while at the anode, oxidation occurs. At the cathode, electron is released and the electron is accepted at the anode. So it is oxidation and reduction, both of them taking place. All right, let's talk about balancing redox reactions. Balancing redox reactions. So how do we go about to balance this particular kind of reactions? Of course, we know that it is always two-way sided. Let's take an example of manganese tetraoxomanganate 7 and iron 2 trioxosulfate 6. Tetraoxomanganate 7 and iron 2 trioxosulfate 6. Okay, we know that from the sound where you have manganate 7, something like O7, that's 4. I'll have -1, or better still, we can have an H, but it's better we just work with the -1 since we're not told what would be in front of it. So we know that this particular compound, if you calculate the oxidation number, we know oxygen will always have an oxidation number of -2. -2 times 4, that will give us -8, should equal to -1 plus x. So when -8 goes to the other side, x equals to -1 plus 8, which is equal to +7. So this manganese at this point is +7. So this also, we are talking about iron 2. So in case of iron 2, we know that when this manganese is reduced, when it is reduced, it will produce manganese oxide, which actually is the 2 states of manganese. It will produce manganese oxide. That's the first thing to note. Then the other thing again is, we know our iron 2, as it is told, we are told it will go ahead to produce iron 3 by oxidation. It will go ahead to produce iron 3. Our manganese 7 will go ahead to give us manganese 2, and our iron 2 will go ahead to give us iron 3. So how do we go about it? The first thing to do is to identify the oxidizing agent and the reducing agent, or better still, or identify the oxidizing part of the expression or the equation and identify the reducing part of the equation. So let's take the oxidation part first. So we have our manganese minus and this. We know that this manganese, of course, needs to be balanced for the equation to actually occur. So we react it with an hydrogen. Of course, it is a reduction. We react it with an hydrogen, and of course, we know that when this reaction occurs, it will lead to the production of manganese 2. Of course, this oxygen would want to create water, so we have a plus H2O. Now, we are having 4 oxygens here, so try to balance out that particular. We will have to put 4 in front of this, and when we put 4 here, we will see our hydrogen has increased, so we have to put 8 in front of our hydrogen, and this expression is looking balanced, but there's still a little thing that needs to be taken care of. If we consider the electrons in the entire system, we'll notice that here we're having -1, here we're having +8, because +1 times 8, and here we're having +2 +0. So since this is balanced, we can forget about it. So we're having a total of +7 here, and we're having +2 here. We need to introduce -5 to balance out the excess electrons. So to balance out the excess electrons, we introduce to the entire setup -5 electrons. Now this -5 electrons, that's the amount of oxidation it receives. That's the amount of oxidation it receives. But for now, we are not concerned about where the oxidation came from. But of course, it concerns us. The entire expression has to be fully balanced. Alright, let's go to the other half equation. This is our oxidation section of the half equation. Let's go to the reduction part. In the reduction part, we have iron 2 becoming iron 3. Of course, iron 2 becoming iron 3, it means it would have lost several electrons. It will have lost several electrons, and logically to say, sorry, this is plus, it will have lost several electrons, that is to say minus about E5, because this one gained 5. The 5 it gained, it has to come from here. Of course, to balance this out, the entire system too must have 5 and 5. So we can try to come up with our completely balanced equation. Of course, the reduction happens on the other side, so you can just put the +5e here. So we can have our balanced equation by merging the two different equations together, and at the end we'll have manganese plus 8 hydrogen plus 5 iron 2 plus 5 electrons would give manganese plus 4H2O plus 5 iron 3 plus 5 electrons. So we see 5 electrons repeating itself, so we can take out the 5 electrons quietly, and then our expression becomes what we have on the board. that's how we go about the balancing of redox reaction. In this particular lesson, we considered types of reactions. Then we looked at the different types of reactions. We talked about combination, decomposition, displacement, double decomposition, thermal dissociation, the redox reaction, reversible reaction, catalytic reaction. We talked about, focus on the redox reaction, and that is the oxidation reduction reaction. We mentioned that they happen simultaneously. The oxidation occurs at one end while the reduction occurs at the other. We also looked at the reducing agents, and we said oxidizing agents are agents or substances which accept electrons, while reducing agents are substances that give away electrons. We looked at electrolysis and oxidation reduction. We noticed that at the anode, oxidation occurs, while at the cathode, reduction occurs. And of course, we just considered how to balance a redox reaction. What are the steps? The first thing is to identify which side is the oxidation, which side is the reduction. Then the next thing is to draw the half equation, or write out the half equation of each of the sides. Then we try to balance out the half equations. Now, after balancing out the half equations, each of them, and then we bring the two half equations together to form one complete equation. So that's how we go about the balancing of redox reactions. Alright, since we've considered this particular lesson, in a few seconds some questions will be displayed on your screen to test your understanding of what has been taught in this lesson. Please attempt them, and if there is any aspect of the questions that prove to be difficult, you can view the video another time for better clarification. Thank you.